Hello, everyone. My name is Sharada Murthy, and I'm a senior product security engineer.
My name is Will Ratner, and I'm a product security engineer. We work at Atlassian, which is a leading provider of team collaboration and productivity software, including Jira software, Confluence, Trello, and Bitbucket. At the beginning of 2021, we undertook the process of implementing container scanning enterprise-wide across Atlassian. Previously, there were some ad hoc container scanning implementations being used by various products in Atlassian with varying scanning tools. Our goal was to ensure complete container scanning coverage across Atlassian using a single, well-defined, and seamless process. We accomplished our goal, but not without having to overcome numerous challenges. In this talk, we'll spend a bit of time covering the platform that we built and how it works at a high level. We'll then jump into the challenges we faced after our scanning platform was turned on, and then discuss the lessons we learned as a result of those challenges. Finally, we'll provide details on our experience so far with having enterprise-wide container scanning enabled for the past 6 months.
First, we'll give a quick contextual overview of containers at Atlassian. We currently have over 2,000 developers and engineers actively contributing to code that runs across thousands of unique containers deployed on our internal platform at any given time. Nearly all of the services built on our internal platform as a service utilize containers, and there's on average of over 2,500 deployments to production a day. Now that you have some context on the scale we deal with at Atlassian, I'll pass it over to Will to talk about what we built to scan these thousands of containers.
Thanks, Sharada. I'm going to take a little time to walk through the scanning platform architecture, as well as some of the nuances we had to account for as we were building this out. I'm going to be somewhat light on the nitty-gritty technical details, as the focus of this presentation is how we fix the systematic issues discovered by the scanner. That being said, we think what we built is pretty cool and want to share it. This is a very simplified overview of the container scanning platform we built. It starts with a service, which can consist of numerous containers being deployed and generating a deployment event that is published to our enterprise event bus. This deployment event includes information like what containers are being deployed for that particular service, who owns the service, and what environment it's being deployed to. We built a small service which ingests these deployment events from our enterprise event bus and dynamically generates Argo workflows that will perform all of the scanning work. Argo Workflows is an open source container native workflow engine for orchestrating parallel jobs on Kubernetes. We use this to define workflows where each step in the workflow is a separate container. For every container being deployed, a scan job consisting of the 5 containers in the red box is executed. And for n containers, we should be executing n jobs in parallel. This allows us to scan many containers at the same time very quickly. The 5 steps in our job are fairly straightforward. The first step processes the raw event further to get additional metadata, like determining if the container has already been scanned, if the container was built using a golden image, or if the deployed container is a known platform sidecar. If the container image has not already been scanned, we then download the archive of the container using a tool called Scopio. We do this because we utilize a shared Kubernetes cluster where privileged mode is not available to utilize Docker and Docker functionality. The downloaded container archive is then passed to Snyk's official Docker container where the scan is performed. Both a Snyk test and Snyk monitor are run. We then add tags to our newly created project in the Snyk platform that include more metadata that is used for reporting. Finally, scan results are parsed and sent to an internal service, which will turn any discovered vulnerabilities into Jira tickets. You might be wondering why we chose to go with event-driven scans over scanning directly in CI/CD pipelines or our container registry. For starters, trying to get thousands of developers and engineers to integrate Snyk into their thousands of pipelines by some kind of mandate would not be a fun time. Our goal was to minimize as much work as possible for our engineering teams. That being said, our hope was that teams would want to avoid receiving any vulnerability tickets in the first place, and so they'd want to integrate Snyk into their pipelines to fix any issues before they deployed. Scanning when an image is being pushed to the registry can be very effective. Unfortunately, we have an internal private registry at Atlassian that did not have a direct integration with Snyk at the time of our project undertaking. Attribution data was also limited in the registry from both an owner and environment perspective. Being event-based means teams get faster feedback when they make changes. When they deploy fixes to their containers, any tickets assigned to them will be immediately closed as patched. If a new CVE is published, we do not have to wait for a team to run Snyk in their pipeline or push a new version of the container for them to become aware of the new issue. Finally, the events we ingest have extremely valuable metadata to help streamline the entire process. It allows us to confidently attribute issues to the right team and provide them valuable contextual information to easily pinpoint where the issue is arising and fix it faster. Other aspects we have to account for when scanning containers is identifying containers built using Atlassian's golden base images or deployed with common sidecar containers. These golden base images are built and maintained by a centralized team at Atlassian. They are responsible for keeping them updated and secure. This allows the teams to not have to worry about issues that may be introduced by this base image and focus only on issues that may be introduced by their own user instructions. The common sidecars are typically containers that are built by many teams at Atlassian and are commonly used by various services across the enterprise. In both cases, we need to make sure any issues found in them are attributed to the team that actually has the means to fix them. So how do we do this? Since the golden base images are not deployed as any particular service, we have an ad hoc scan that runs daily and ensures any issues that may be found are assigned to the team that manages those golden base images. We then need to determine if the containers being deployed are actually built on these golden base images. Initially, to do this, we simply compared the layer information of the service container being deployed to the layer information of all of our golden base images. This works fine for a small number of golden base images, but as that number grows, it becomes far less scalable. We found instead that it was much easier to have the golden base image teams include Docker labels when building their images so that we could check and verify much faster. It allows us to determine what golden base image is being used as well as the version. This is important because it helps us ensure that teams are using the latest safe version of a golden base image. We use a similar process when dealing with common sidecars as well. If a service is using an outdated sidecar or built the application on an outdated golden base image, but neither of them have vulnerabilities, then they can continue using them. However, if the outdated version being used by the service contains vulnerabilities, then teams would receive a ticket requesting that they update their base image or sidecar deployed with the service. I've mentioned ticketing a few times and want to dig in a little deeper on how we use Jira tickets after a container scan is complete. Once we've scanned the container image, we group all of the issue data by the vulnerable packages. This ensures our internal ticket creation service will create one ticket for each vulnerable package that needs to get fixed. This is so that we do not overwhelm teams with hundreds of tickets that likely require the same fix. We could, of course, just have teams with one ticket and ask them to upgrade all of their packages, but sometimes that's not always feasible right away. For example, a team may be able to easily upgrade some OS packages, but more work may be required for a specific package that would cause breaking changes to their application. We found the per package level of granularity as a good middle ground when creating tickets. Once the tickets are created, they end up in our vulnerability funnel. This is where all vulnerability tickets land from our automated scanners, bug bounty program, and various other sources. There could be an entire separate presentation on our vulnerability funnel, but I'm going to highlight some of its core functionality that's important to container scanning. When a ticket lands in the vulnerability funnel, it already has an owner assigned. The vulnerability funnel has automation that includes additional team details to the ticket and sets the remediation due date based on the severity of the issue. The owner is notified that they have a vulnerability ticket that needs their attention and when it needs to be resolved by. Additional notifications are sent out as deadlines approach to help ensure these issues are resolved in our defined service level objectives for vulnerability remediation. All vulnerability tickets must be patched within our publicly defined service level objectives based on the severity of the issues as listed here. Teams at Atlassian work incredibly hard to ensure these SLOs are not breached. So now to set the stage, we've built out our container scanning platform and have flipped the switch to let it run. This led to a slew of challenges that we would need to overcome in order for this work to be successful and not lose the trust of our product teams.
For starters, we created too many tickets for our teams. We knew ahead of time that many tickets would be created, but we chalked it up to the fact that this was our first time doing container scanning. Combine this with the fact that typically remediating these container package vulnerabilities is fairly straightforward. We didn't see this to be a huge problem. Unfortunately, that is not how it was perceived by the teams. The per package tickets were seen as individual issues that needed independent fixes. This was not actually the case, but we failed to communicate that fact effectively. This led to concern that there was too much work to remediate all issues within our SLO. On top of the sheer amount of container vulnerability tickets created, there was also a lot of confusion on how to fix these issues in the first place. Because this was the first time we were scanning containers enterprise-wide, many teams were confused on how they were supposed to fix issues. Do they need to update their entire base image? Can they just upgrade the specific packages that are vulnerable via the package manager? Or would it be better to move to a slimmed down base image that removes the packages entirely? When teams would look up more information on a specific issue in Snyk, they would see instances where Snyk severity was low, but the CVSS score was critical. This led to many questions and manual work on our end. Because we only filed tickets for critical severity issues, teams were equally stressed by the number of tickets combined with a short time frame to fix them. Finally, we discovered that there were a lot more common sidecars at Atlassian than what we had originally thought. This meant we needed to track down owners and ensure any tickets were reassigned to the teams responsible for those sidecars. All of these things resulted in a less than ideal experience for both the security team rolling out tickets for these issues and the engineering teams tasked with fixing them. We knew we had to provide a better experience for our teams. We stepped back to look at the primary pain points of our process and set out to resolve them. To combat confusion, we documented and communicated our best practice for building containers and provided examples for numerous operating systems on how to upgrade and remediate vulnerable packages. We encourage teams to utilize golden base images whenever possible. When not possible, we help them with the adoption of distroless containers or other available minimal container base images. All of this information was included on the tickets that were created and resulted in significantly less questions and quicker actions from engineering teams. We identified the most effective teams and provided them hands-on help, such as updating their Docker files directly or working with security champions and developers one-on-one. We were able to show them how a single line change to a Docker file would close out 20 or more tickets in one go. This helped us regain their trust and helped us propagate this information to other teams throughout Atlassian. We examined which specific issues teams had the most questions about and realized it was any issue where a clear-cut fix was not provided or was not available. This led to us making the decision to change how we file tickets altogether. If the scanner did not provide a fixed version to upgrade a package to, then we did not file a ticket for that package. We also chose to utilize Snyk severity score rather than CVSS, as it seemed to better represent the priority needed by the engineering teams. This resulted in a drastic drop in the number of tickets filed, quicker resolution of the remaining tickets, and much happier engineering teams overall. Rolling out container scanning enterprise-wide was a learning experience from start to finish. Some things we learned will make us better at implementing various security scanning tools in the future, and others were more specific to container scanning. We want to highlight two core learnings and how they helped us remediate thousands of issues in our containers.
This may seem obvious, but fixes suggested to engineering teams need to be clear and actionable. Sometimes a fix may seem clear after doing a little research, but that just adds additional overhead to the teams who already have a lot on their plates. For example, telling teams to upgrade or slim down their base images is typically good advice. However, trying to make that clear and actionable programmatically is not always possible, especially at scale. It's difficult to determine what base image a container might be using in the first place without the Docker file, which makes upgrade recommendations error-prone. It's likely that teams just need to upgrade their packages via the package manager to fix any issues. That being said, it should be encouraged for teams to look into using a better base image if applicable, but that's a decision they can make on their own when time permits. It's also important to ensure that when recommending a fix, that you are recommending the latest or nearest safe version of a package. Many tools will just recommend the nearest version fix for a particular issue. Upgrading to that version may fix one vulnerability in a particular package, but could end up introducing even more. For example, with this particular curl CVE, it's recommended to upgrade curl to version 7.64.0. But when we examine the 25 most recent curl versions and which releases that are vulnerable, we see that 7.64.0 actually has 20 publicly disclosed vulnerabilities associated with it. Although the web page with the remediation details says or higher, the API actually only returns 7.64.0 as the fixed version, which is what we originally used when our tickets were created for teams. The quickest way to lose a product team's trust is to tell them to upgrade to a specific version in order to close a ticket, only for that fix to open up 20 more tickets. Because of this, we typically recommended teams to upgrade to the latest version of a package, assuming it's not a beta or development version. We also found that even with a clear and actionable fix, it's not always obvious what needs to actually be done to action that fix. Not everyone knows how to upgrade packages in their containers or what base images they should be using. This led to us writing very thorough documentation for various operating systems on how to update, upgrade, and remove packages. Yes, all of that's typically a Google search away. However, adding it directly into the tickets that are requesting teams to fix these issues allowed us to take one potential step out of their remediation process, allowing them to fix issues faster. The other major lesson we learned specific to container scanning is that we should trust the distros when it comes to vulnerabilities in their respective operating systems. Traditionally at Atlassian, we have used CVSS exclusively to assign severity to vulnerabilities and their subsequent remediation SLOs. However, when rolling out container scanning, we noticed that Snyk actually provided us with more data than just the CVSS score that they use to calculate their own severity. They utilized Debian and Ubuntu's own priority scores to determine the relative importance of issues when possible. While CVSS is a great system, using only the base score loses out on a lot of context and can lead to developers dropping everything for an issue that doesn't actually warrant that kind of response. For example, with this CVE, you can see it has a critical CVSS score. However, Snyk is flagging it as low severity. When we dig deeper and look at Debian's security tracker, we can see they actually consider this issue as unimportant. In fact, it's not even treated as a security issue by the upstream. As a result, there's been no fix implemented and there likely never will be. Because of this, there's no reason to try and get our teams to figure out a fix for this themselves. Because we could access the distro priority programmatically, we wanted to use it. I'm personally not a subject matter expert on any particular Linux distro. I would much rather leave the analysis of these CVEs in the context of a specific distro up to the experts. Debian and Ubuntu both have designated security teams that are paid to handle and examine these issues. Due to the prominent usage of Linux throughout the world, we feel confident that the priority given to these issues are in the best interest of the distro, and we trust the respective experts to make that decision. That being said, when this data is not available, we do fall back to using CVSS scores. It's not often that automated scanners find issues that are truly drop everything and fix right this second. Utilizing the distro's priority score helps ensure that we are not putting our teams into an urgent situation that doesn't deserve one. It helps build trust with our teams, knowing that the time in which they need to remediate an issue matches the risk associated with the issue. Asking our teams to fix an issue in 2 weeks that the distro considers low priority or negligible does not seem like the best use of their time. And that sums up our experience of implementing container scanning at Atlassian. It was a learning-filled experience with a few bumps in the road. That being said, after scanning and remediating container issues over the past half a year, we have seen additional benefits besides just improving Atlassian's security posture.
Because we provide teams with clear and actionable fixes, the security team gets significantly less questions. This frees up time for us to focus on other work and also empowers our team to remediate any issues that might pop up in their containers on their own. We have also seen a much larger adoption of Snyk in teams' build pipelines. This would have been a challenge to enforce across the company, but teams are seeing the value in catching issues before they might deploy their containers. Integrating Snyk into their pipelines allows them to avoid receiving tickets in the first place and saves them much more time down the line. Teams also began seeing the value of using our golden images. Not only would they not have to worry about receiving vulnerability tickets when they are using golden images, but they also got the benefit of many additional tools and services baked into the golden images. It has led to teams asking for more golden images for various tech stacks, which will only help improve the centralization of container security at Atlassian. Finally, many teams noticed significant operational improvements when going through the process of remediating container vulnerabilities. Typically, teams would find that they were not using the majority of the vulnerable packages and could switch over to base images that removed them altogether. More teams began utilizing multi-stage builds that ensured their final images were as bare bones as possible, leading to much smaller container image sizes. Smaller containers, in turn, led to faster builds and faster deployments. Thank you all for giving Will and I the opportunity to share our experience with you. Should you have any questions about implementing container scanning at scale or anything else, please feel free to reach out to either of us via email.